Exactly. Hi there. I hope you can see my one slide PowerPoint before I jump to the Jupiter.
That looks
And
great.
it all indeed dates back to last year PsyCon, which was the last chance to see most of you in person. Things get lonely these days. And then I got super excited about the marriage between Psi4Education and Psi4NumPy and Jupyter notebooks, and promised to do something about SAPT, which I initially thought would be to, say, turn some of the SAPT tutorials into a Psi4Education module, which I clearly realized for exactly the reasons that Ashley gave today is maybe not the ideal thing. So Psi4NumPy has, of course, many excellent examples and tutorials. As far as SAPT is concerned, we owe these examples to Daniel Smith, Jonathan Waldrop, and I wrote a few as well. And I really like them as an introduction to programming new SAPT expressions. So when there's a new graduate student in the lab who need to learn the under the hood details of SAPT, I think the Jupyter tutorials are the best resource I can offer them. But I don't think there's any undergraduate class who really needs to delve into the details of programming SAPT expressions. So I realized that it would be useful to do something at a more general level for Psi4Education that's still related to weak interactions. So I decided to do something a little bit simpler, so there's no code overlap between the Psi4NumPy tutorials and this module. I just wanted to help students learn how to calculate and interpret basic non-covalent interaction energies, and both with supermolecular methods and with SAPT, and how to make sense of the results that we're getting. So there will be some graphs. Thanks to Laurie, there'll be a ternary diagram at the end, which I personally really like. So let me finish this PowerPoint thing and see if I can now. All right, so that's the instructor version. So everything here is pre-filled, and we're gonna look at the two simplest and most obvious examples, the helium dimer first and then the water dimer, and we can obtain a potential energy curve and look at the character of it. So we define a bunch of distances, and at first we run a supermolecular coupled cluster interaction energy for that in a small basis set. So I guess that takes up to a minute, but once we have it all done, we have the potential energy curve, and for a good reason, of course, we plot a Hartree-Fock curve, which is qualitatively inaccurate because there's no attraction, there's no dispersion, and then a cluster curve as the real thing. So the students get to reflect on what's important for these interaction energies and things like, why does helium form a liquid at very low temperatures? After all, you do need some attraction in there. So once we've done a supermolecular curve, we can move on to SAPT. And there's a little introduction. There's just SAPT0, of course, the simplest possible level. We're going to run the same curve and get a graph with all of the SAPT contributions, and we want to be able to distinguish, to understand what these are, what's electrostatics, what's induction, dispersion, and exchange, and how they compare to the total energy. So, of course, one particular important part is the long range. So what's long range and what's short range? And one, say, additional feature of Python beyond the prerequisites that comes in here that students need to learn a bit is basic optimization here from SciPy, where we're trying to answer the questions. So we have these dispersion energies, and we've maybe learned that the dispersion energy vanishes at long range like the inverse sixth power of the distance. So here we're just fitting the optimal inverse power of the distance to a bunch of long-range data for dispersion energy, and 6.3 is pretty close to 6, so I think that works pretty well for demonstrating what's going on in long range. So then we move on to the water molecule. We're not going to wait for coupled clusters in here, so we'll run a quick MP2 potential energy scan. That's running right now. Now the students have to fill most of these definitions. So we give them the dimer, and they need to extend it into a supermolecular calculation. So we should be done with it in a couple seconds, and then we'll do SAPT as well. And the difference, we once again want to look at the long range and fit some powers, optimal inverse powers, to the to different SAPT components. Now, of course, we have two polar molecules, so we expect a dipole-dipole interaction, and we can interpret the electrostatic energy in this way. I see these things go a little bit quicker without blue jeans, but well, I'm also actually have a pre-computed SAPT graph in here. And once we have these curves, both for the supermolecular and the potential energy, again, there's a whole lot of nice questions that we can answer. Yeah, here it goes, especially about the long range. Quick. So, and then maybe that's not the best structure, but we go on a little tangent that familiarizes students with calculating bond lengths and bond angles, which is helpful to understand a thing that might seem weird for the students at first. So we have these two waters, and we do a supermolecular calculation. These two waters are exactly the same, but we're getting slightly different energies for the two. And how is it possible? So the students write a little code to find the bond lengths and the bond angles in the water molecule using the Cartesian geometry, and verify that these are exactly the same, while the MP2 energy for one molecule and for the other is different, which is, I think, a nice illustration of the basis set superposition error and how we take it into account in the calculation, because even if this molecule is the same, the other molecule with ghost basis centers is in a different location depending on which one we pick. That's all super quick. So the students can verify that, yeah, these two other molecules look exactly the same, but there is a tiny difference in the energy of each, which we can track down to the dimer basis and ghost basis centers. All right, so here we can do the same thing as we did for helium and fit the optimal powers for different SAPT components. And we would expect a 6 for induction and dispersion because we have two neutral molecules, and 3 for electrostatics because we have a dipole-dipole interaction at long range. And I think it's very important to understand that SAPT is not just what SAPT gives for electrostatics is not just a dipole-dipole interaction. And for this purpose, we quickly calculate the dipole moments for each water molecule at the Hartree-Fock level. And now the students, using the theory provided, can write a formula for the dipole-dipole interaction. And now we can compare the entire SAPT electrostatics with just the dipole-dipole term. And we expect, of course, the same behavior at long range, but at short range, charge penetration effects, which several people here at this conference have very nicely elucidated, kick in and change the behavior. All right, so we're almost there, just a little bookkeeping. Analyze the sapped contributions to the water dimer in the minimum. As first, maybe in freshman chemistry, students learned that the interaction between two waters is mostly dipole-dipole, or hydrogen bonding is mostly dipole-dipole, and now we see that there's a sizable contribution of induction and dispersion in there. There's some summary table for the students to fill in. And for the very last point, so in the course of this lab, we have generated two potential energy curves, one for the helium dimer, one for the water dimer, and we have calculated subcomponents for all of them, for every point on the curve. So we can use the code straight from Lori and from Psi4 for the ternary diagram, and we can plot all of these values in two different colors for two different systems, all the points that we have calculated with SAPT. And as expected, the red points are the water dimer, which is primarily bound by electrostatics, especially at long range. And all the blue points are the helium dimer, which is bound primarily by dispersion. And just as an illustration to the students, we show a similar diagram for just all the water dimers you can imagine. These are 2,500 water dimers, and depending on the orientation, are dipoles favorable or not, you can get all kinds of points on the diagram as well. So